In order to understand the crystal structure, we need to take a look at a more abstract concept, the Bravais lattice. So we start the treatment of crystals with this more abstract lattice concept. So what is a Bravais lattice? It is an infinite array of discrete points in space with an arrangement and orientation that appears exactly the same from whichever point the array is viewed. So in other words, it has translational symmetry. So when we go from one point in the lattice to the other point, and when we look around, we see that the arrangement and orientation of the points are exactly the same. A three-dimensional Bravais lattice consists of all points with position vectors r of the form n1a1 plus n2a2 plus n3a3, where a1, a2, and a3 are three vectors that are not all in the same plane, and n1, n2, and n3 are integers. So in order to go from one lattice point to another lattice point, we need to have a translation vector that includes integer multiples of these three vectors. Now, as an example for a Bravais lattice, we can consider the square lattice. You can see that the a1 and a2 vectors are defined, and from point A to point B, I just need to have one a1 vector displacement, and from point A to point C, I need to have a1 plus 2a2 in order to reach this point. So going from point A to point C, I see that when I look at the lattice from point A versus when I look at the lattice from point C, the environment looks exactly the same. Therefore, it's symmetric, and so we say that the square lattice possesses a translational symmetry, or the lattice remains invariant under any translation. Therefore, it must be a Bravais lattice. On the other hand, when we look at the Honeycomb lattice, you can see it here, and I have defined the directions as north, south, west, east, and northeast. So when I go from point A to point C in the Honeycomb lattice, and when I look at the northeast direction, I see exactly the same thing. However, when I go from point A to point B and I look at the northeast direction, the view from point B is quite different from the view from point A. So we can basically conclude that the Honeycomb lattice is not a Bravais lattice because it doesn't have this translational symmetry. If I go from point A to point B, the lattice would look exactly the same if I rotate the page by 180 degrees. So from the same point of view, I'm not getting the same view of the lattice. Okay, so this was an example for a non-Bravais lattice. Now, when we have a Bravais lattice and we assign to each point in the lattice a unit consisting of one or more atoms. So we are going from the abstract concept of the lattice to a real crystal structure by assigning a unit that consists of one or more atoms. So each such unit is called the basis, and when we add the basis to the lattice, we obtain the crystal structure. You can see here I have a square lattice, and my basis consists of two atoms in this manner, and when I put those atoms in the lattice points, I obtain the crystal structure, and points A and B on this crystal structure are not equivalent. So if I look at a lattice that is created by assigning a basis to a Bravais lattice, I know for sure if the basis consists of more than one atom, the Bravais lattice turns into a non-Bravais lattice. So this is an important feature of the Bravais lattice. Now, the set of vectors a1, a2, and a3, whose integer combinations will span the whole lattice, are called basis vectors or primitive translation vectors. So here is my square lattice again. So I can think of two basis vectors a1 and a2 in order to travel between lattice points inside, or I can use a1 and a2 prime, which is the diagonal vector. So these primitive translation vectors or basis vectors are not unique. So if I go from point A to point B, my displacement vector will be a2, or I can think of a2 prime minus a1. So a1, a2 and a1 and a2 prime are both primitive translation vectors. So this choice is not unique, as you can see. So that's basically my remark. The choice of primitive translation vectors is not unique. Now, when we look at a lattice and we're trying to find a structure that is repeating itself in a periodic manner, we can find some unit cells. So it consists of, with a proper choice of lattice vectors, a volume of the space can be translated and fill up the whole space without overlapping itself. So this is called a unit cell. So you can see here in the square lattice, cell 1 and cell 2 are all unit cells. But there is a difference between cell 1 and cell 2. Cell 2 includes only one lattice point, so it's called a primitive unit cell. So a special unit cell is a primitive unit cell that is the parallel piped defined by the primitive translation vectors and is the smallest possible unit which can build up the lattice by periodic repetition. So primitive translation vectors should be building the primitive unit cell and build up the lattice by periodic repetition in the smallest possible unit. So a primitive unit cell contains only one lattice point. This is very important. If I look at cell 1 and cell 2, which are both unit cells, so I can see that I have 4 atoms at the corners. So 1/4 of each one is within the cell. So 1/4 times 4 from the corners. And then I have 2 atoms at the edges, edge centers here. So half of those are within the unit cell. So 4 times 1/2 from edge centers. And there is one point in the middle that is the center point. So I have to add that one up. So I see that I have 4 atoms per unit cell. For cell 2, I have 4 atoms at the corners. So those are here. And I have 1/4 of each included in the cell. So it has only one cell. Therefore, it's a primitive unit cell. Now, if there is a basis that is assigned to this lattice, the primitive unit cell does not contain one atom, but it contains one basis. So it would contain 2 atoms if there are 2 atoms per basis, etc. So this the number of atoms in the primitive unit cell can be 2 or more. It depends on the basis. The important thing is that there should be only one lattice point, not only one atom. In 2 dimensions, the area of the primitive unit cell is found by A1 cross A2, these 2 primitive translation vectors cross product magnitude. So for square lattice, that would be A1, A2 sine 90, for example. In this example, you can see that the angle between these is 90 degrees. So that would give me A1, A2, which is the area of the square. In 3 dimensions, the volume of the primitive unit cell is A1 dot A2 cross A3. So that's the volume of the parallel piped, basically. And as you can see here I have an oblique lattice. I can choose primitive unit cells in different ways. So this choice of the primitive unit cell is not unique either. And that's because the choice of the primitive lattice translation vectors was not unique. The choice of the primitive unit cell is also not unique. So if it is not unique, is there any scheme to obtain a primitive unit cell for a given lattice structure? The answer is yes. It's called the Wigner-Zeit primitive unit cell. And the procedure is as follows. We take a lattice point and draw lines to connect it to its neighbors. So here I have chosen this lattice point at the center, and I have connected it to its nearest neighbors. So you can see those dashed lines here that is connecting it to its neighbors. And then at the midpoint of each line, draw new lines or planes in 3 dimensions, normal to the connecting lines or connecting planes. So you can see that I look at the midpoint here and I draw a perpendicular. So here is one perpendicular that I'm drawing. Here is another perpendicular I'm drawing. Here is another perpendicular at the midpoint. Here is another perpendicular at the midpoint, etc. Then I look at the smallest volume in 3 dimensions or smallest area enclosed by these boundaries, and that gives me the primitive unit cell that is called Wigner-Zeit's primitive unit cell. So that would be this square in the middle. So I basically show this area with these blue lines, and you can see that I was able to find that the Wigner-Zeit's primitive unit cell of the square lattice is a square. Now, in 2 dimensions, the Wigner-Zeit's primitive unit cell is always a hexagon unless the lattice is rectangular. So square lattice is rectangular, so it was not an hexagon. But here you can see for a general lattice structure, if you follow the Wigner-Zeit's procedure, you draw the lines connecting the center atom to its nearest neighbors, and then look at the midpoints of each line and draw a perpendicular to each line. You can see that the smallest area enclosed by the boundaries is given by a hexagon. Okay, so this is a general feature in 2 dimensions. How about a conventional unit cell? A conventional unit cell is not necessarily a primitive unit cell. It's in general a non-primitive unit cell, but it captures the symmetry of the lattice. So here's a good example, body-centered cubic lattice. We have 8 atoms at the corners, 1 atom at the center, or if this is a lattice, then 8 points at the corners, 1 point in the middle. It's not a primitive unit cell. However, it captures the symmetry of the point in the middle, so it is conventionally used to describe the body-centered cubic lattice structure. And the numbers that specify the size of the unit cell are called lattice constants. In the body-centered cubic structure, here the distance between 2 points in the lattice, for the nearest neighbors, we have not nearest neighbors, because the nearest neighbors would be the middle atom and the corners. Well, between 2 corners, for example, we have a distance a, and a is called the lattice constant. Then you would find that the distance between the midpoint and the corner would be a square root 3 over 2, which is less, so that would be the nearest neighbor distance. Okay. So we looked at the basic features of the lattice structure. The concept of Bravais lattice is very important. It's basically describing an abstract, in abstract space, an arrangement, a periodic arrangement of points that appears exactly the same from whichever point this array is viewed, both from the arrangement and orientation point of view. So that means it has translational symmetry. The lattice remains invariant under any translations. And the displacement vectors between 2 points in the Bravais lattice are given by integer multiples of 3 vectors. And a good example is the square lattice, where we have the translational symmetry. And a good example for a non-Bravais lattice is the Honeycomb Lattice. You can see here, looking from point A and point B, we have a completely different view of the lattice. If you look at it in the northeast direction, therefore it's a non-Bravais lattice. If we assign a basis that consists of two or more atoms to each point in the lattice, we obtain the crystal structure. And when we turn a Bravais lattice into a crystal structure and we reconstruct a lattice consisting of the new points that we have assigned, the new lattice, crystal lattice, is not Bravais. So it's going to turn into a non-Bravais lattice. So the underlying lattice structure is Bravais, and then we have the basis. Or if we consider all of the points created by the points that we have introduced in the basis as well, it turns into a non-Bravais lattice. Now, this set of vectors whose integer multiples allow us to translate between lattice points are called basis vectors or primitive translation vectors. So we can, and the choice of these primitive translation vectors is not unique. So we can have A1 and A2 or A1 or A2 prime as these vectors. Well, you can see that 2A2 prime cannot be used here because you would need a 1/2 to go from one lattice point to another lattice point. So we have to make sure that these are as small in length as possible because we need integer multiples of these to travel within the lattice. And the choice of these primitive translation vectors is not unique. And when we look at the possible unit cells that we can define, well, we have two types. We can have unit cells that do not overlap itself and can fill up the whole space. However, it does not have the smallest possible volume in 3D or area in 2D. The one that has the smallest, that occupies the smallest amount of space is called the primitive unit cell. And the primitive unit cell, by definition, contains only one lattice point, or if this has been turned into a crystal structure, it contains only one basis. So it can have more than two atoms. However, it has only one lattice point for the underlying lattice structure. And here you can see in this example, cell 2 is a primitive unit cell because it contains one lattice point, 4 times 1 over 4 from the 4 corners. So in 2 dimensions, we talked about this. The area that is spanned by the primitive unit cell is A1 cross A2 magnitude. In 3 dimensions, the volume is A1 dot A2 cross A3. That's the volume of the parallel pipe. And the choice of the primitive unit cell is not unique. However, there is a procedure that gives us the same or well-defined primitive unit cell that everybody would agree on. That is the Wigner-Seitz primitive unit cell. And that is found by connecting a center atom to all of its neighbors, nearest neighbors, and drawing perpendicular lines at the midpoints of each connecting line and finding the smallest area in 2D or smallest volume in 3D enclosed by these boundaries. So that would be our Wigner-Seitz cell. And in 2 dimensions, all Wigner-Seitz cells, or Wigner-Seitz primitive unit cells, are hexagons for non-rectangular lattices. In addition, we can talk about a conventional unit cell that is not a primitive unit cell per se. However, it captures the symmetry of the crystal, so it is preferred in discussing the crystal structure. For example, in the body-centered cubic lattice, you can see that if I calculate the number of lattice points here, this would be 1 over 8 times 8 from the corners and 1 in the middle center atom or center point. This would give me 2 points per cell, and that therefore it's not primitive unit cell. However, it does capture the symmetry of the point in the middle, therefore it's preferred. And we use lattice constants to define the size of the unit cell. For example, in the body-centered cubic structure, the distance between two points at the corners is A, the lattice constant that we have introduced.